Howdy. This is our MXET 375 final project. And for our final project, we have decided to create and simulate a trebuchet. We are group number 5, section 902.
For the description of our project, we are creating a trebuchet. A trebuchet is a mechanical system that utilizes linear force to convert to rotational energy, which is then converted back to a linear force that acts as a vector to provide a payload object with a projectile motion and trajectory that will allow it to fly a certain distance when affected by gravity. Once the payload leaves the trebuchet, it will be in free fall, so its motion will be easily modelable in an equation of motion. How this will work is we'll use a rotating arm attached to a counterweight and sling to launch a mass of a payload varying distances based on the amount of counterweights we apply to the system. The counterweight drives the beam forward by its mass being directed downwards. And what it does is it causes a rotational motion to be experienced on the sling, which, whenever it reaches an angle at the top, the hook element that attaches to the other side of the sling's pouch will reach an angle to where it is no longer in contact with the trebuchet arm itself. How this will work is that angle will be something that is calculated and factored into our equations of motion, and the input force will be our weight. And the output from this input force would be the amount of distance. This model will be scaled down. So 3D printing is the main manufacturing method to develop this prototype. Since the mass is our input for this system, a fixed amount of increment can be used to change how much mass the trebuchet will experience, therefore changing each output distance the payload is flung by the trebuchet itself. The sling, hook, beam, length, and all of these various aspects that can affect the trajectory of this motion will be fixed because it allows for a simplified version of the system to where mass is the only thing that influences any of these parameters and the output of its distance itself.
For our project, we divided the execution into three main parts: mechanical, electrical and computer, and simulation. The first section we have is the mechanical section, where our first step is to use Fusion to model our system to give us an idea of what the system will look like and guide us on how to build it. This will then lead us to our prototyping and troubleshooting phase. In this section, we're going to and test our design to make sure that everything is built properly and to make sure no major errors pop up while making the physical model. This will then lead to the testing and data collecting part. And in this area, we're going to be doing test runs of the trebuchet and using a web tracking app to track the position of the pouch and the position of the counterweight. This information will then be compared to the simulation data in the next section. Next is the electrical and computer section. This section is where we're going to be doing motion tracking of the payload and the counterweight, using the position tracking app mentioned earlier to record the position as the weight falls down and as the pouch completes its full rotation upon the release of the payload. This will give us a detailed picture of how the trebuchet behaves during operation. The last section we have is our simulation. In this section, we're going to import all of our collected data from the experimental run and the Fusion model into Simulink, and our goal is to identify what parameters are needed to have the same results as the experimental run. Our goal is to be able to see how the changes like increasing counterweight affect its performance. By moving from modeling to building to simulating, we'll get a full understanding of how our trebuchet behaves and how to improve it.
All right, and so then that leads us into our distribution of work. And so for this project, there were like three main categories of, I guess, kind of tasks that needed to be done. So there was like the research and the equations of motions. There was the Simulink modeling, and there was the 3D modeling within Fusion. And so Daniel is going to work on researching kind of the trebulation system and how that kind of works. And so from that, he'll be able to derive the equations of motions for it. And so these motions will be the ones that we use for Simulink. And so he's gonna take those equations and work with Jackson to kind of use that to model the system within Simulink. And so Jackson's also going to be working on the project presentation that is due at the end of the project. And his main task, however, will be the simulation within Simulink. For my part, I will be modeling the trebuchet within Autodesk Fusion. And from there, we'll be able to 3D print the model, and we can create prototypes and just kind of run a few test runs and troubleshoot any issues that we encounter. And so from this 3D model, we can also take that and import it into Simulink. So to kind of compare it to the simulation model and to just kind of see how that works.
For our timeline, it was just broken off into 3 sections. The first section we have is research and planning. This is going to be my section. This is where I'm going to be.
For our timeline, we've broken the project down into 3 main phases: research and planning, modeling and simulation, and data collection and presentation. In the first phase, I'll focus on researching the trebuchet mechanics and planning how we'll implement the equations of motion into Simulink. I'll start by studying how the trebuchet works and identifying its key components. This includes how the system rotates and generates torque, and identifying the role of each of the components, such as the arm, the counterweight, and the sling. This part is crucial since it is the foundation for our simulation, and without it, we won't be able to accurately simulate the system at all. From there, I'll work on delivering the equation of motion, making sure to include all the necessary inputs and outputs. The goal is to produce equations of motion that are accurate enough to be able to simulate the system. Once the equations are ready, I'll collaborate with Jackson to figure out how we'll bring them into Simulink for the next phase. In the second phase, we'll focus on building the simulated and physical models. Martin will take the lead on designing the trebuchet in Fusion, making sure that it fits the proportions we expect. Once the design is complete, we'll import the model into Simulink, where Jackson and I will work together to establish the block diagram and its parameters to be able to simulate it. We'll also begin 3D printing and prototyping, using the Fusion model as a reference to build our trebuchet model and ensuring it behaves as expected. By the end of this phase, we should have both a working simulation and a physical trebuchet ready for testing. The final phase is all about testing our model and analyzing our results. We'll run real-life tests with our trebuchet, and we'll be collecting data on the motion of the pouch and the counterweight using the position tracking app. This will be able to give us real-time information on the position of the pouch and the counterweight. This experimental data will then be imported into Simulink, where we'll compare it to our simulation results to validate the model. If need be, this is where we'll fix any issues with our simulation or model to produce accurate results. Finally, we'll wrap up by preparing our presentation, ensuring to summarize everything from our research, design, and testing and simulation to give a good presentation.
The expected outcomes of the trebuchet system expects it to be able to launch a load multiple times without any major failures that could influence it not being able to operate anymore. Simulated position values of the pouch will resemble measured experimental values whenever we will measure the projectile motion of the trebuchet whenever we are testing the prototype. The simulation will reveal also how changes in this counterweight's mass will affect the projectile motion, i.e., resulting in a longer thrown distance by the catapult when a larger mass is utilized, as that's the expected theory of how this object works. Just as discussed before, the EMMs will use our weight of the countermass as our input variable and the projectile distance being flung as the output variable. And this will allow us to determine multiple parameters and constants that are attributed to the functioning of the prototype itself, which will then be rendered in Simulink via using multiple testing to extrapolate what these parameters themselves are. Thank you for watching. I hope you enjoyed our project presentation and gig 'em.